Hello there, ATS EVS 105 students. Dr. Shruggy here, and we're ready to take on what might have seemed like a really important thing right from the beginning of the semester, and that is to talk about what is the future of climate. I'm guessing that the answer is not exactly going to be a huge secret for you, but how did we get there, and what does this tell us, and so on, is what we're really doing in this module. And to understand what we're going to be saying about the future climate, we're going to need to understand what the changes that are going to be happening to the atmospheric constituents, in particular greenhouse gases, in the future. Well, okay, and we know from what we've learned all through the semester that the most important one of those greenhouse gases is going to be carbon dioxide. So what determines the actual amount of carbon dioxide that's being emitted by society in any given year? Well, your textbook actually breaks it down into three kinds of terms. It's going to be population, affluence, and technology, where population is just the total global population. The more people there are in the world, the more consumers we have, and all these products and services that they can be consuming, all of which, or at least much of which, either took carbon intensive technologies like burning of fossil fuels to make or to consume. And so, well, obviously the population is going up at a ridiculous rate. I mean, of course, now this is a very long scale in this diagram, but you can see we're spiking the population right around 7 billion right now. Even if you choose it to a much narrower period of time, just the last few hundred years, you can really see the dramatic uptick in global population starting around the year 1900. That's intrinsically a good thing, right? I mean, we're not in any way saying that it is a bad thing that population is growing, but that is something that we have to take into account when we are trying to address and understand climate change. Affluence is related to that as well because, I mean, the richer people are, the more they consume. By definition, being rich means you have stuff or you consume services or whatever. And while it's true that that can be more vehicles, more mileage, more airline travel, and so on, you know, for a large part of the world that just means more meals, or that might mean more ability to get to a good job, or more access to healthcare, whatever. But all those things require fossil fuels. At least in our present economy, all those things require fossil fuels. And so affluence is something else. Again, nobody's saying that that's a bad thing. It's not a bad thing that the world is becoming more affluent with time, and fewer and fewer children are dying of hunger, and more people have access to healthcare and so on. That's an intrinsically good thing. But it is something that we have to understand when we're going to be addressing and understanding climate change. And when we're talking about technology here, we're talking specifically, not so much like as in fancy new computers or something like that, we're talking in general about techniques and so on for changing the amount of energy it takes to produce stuff. You know, it may or may not, it may take a greater or a lesser amount of energy to produce each car, or to produce each whatever kind of gadget or whatever you're talking about. And if we can use technology to make the production and distribution and use and so on of these different pieces of technology, these different consumable goods, to make it all less energy intensive, that's intrinsically a good thing. Now, of course, in our world, most of that energy is coming from fossil fuels, so whenever we can find ways to make processes more efficient and products more efficient and so on, we are intrinsically also reducing the greenhouse gas, the carbon footprint and so on of that technology. And in fact, we're actually fairly good at that. In fact, across the last couple of decades, the energy intensity, we'll learn about that term in just a little bit, but it's part of this idea of technology, has actually gone down. The amount of energy it takes to produce $1 worth of goods and services has generally, albeit slowly, trended downward over the last few decades. It just makes sense. It's a cost management issue if you are in industry. Everything you can do to make processes slightly more efficient makes your product more profitable. Everything I showed you so far has been kind of touchy-feely, but it can be quantified into an equation. I equals P times A times T. In this equation, I is a symbol that has to do with the total emissions of greenhouse gases into the atmosphere. In your textbook, I believe they did it in like tons of carbon. As the way I'm going to be developing it here, which came from a different paper, it's going to be tons of carbon per year, but you get the idea. The left-hand side of this equation is about adding carbon to the atmosphere. This has the clever name of being the IPAT relation, just because it looks like IPAT on there. It's more accurately called the Keio identity. I can't remember his first name. Keio is a Japanese engineer and economist who developed this as part of his understanding of use of energy technology. P in the symbol is just the global population, just as units of people. Okay, presently our population is about 7.1 billion, and it's on its way to, we're not sure. We're going to have to figure that all out. A is global affluence. This is usually measured in terms of like the gross domestic product per person for the whole world. So it has units of like dollars per person. It's effectively how much each person on Earth produces in a year in terms of dollar value. And then that T is the greenhouse gas intensity. It's how many tons of carbon it takes to produce a dollar's worth of goods. And of course, it could be different, kilograms of carbon or whatever. But your units work out then to be tons of carbon per dollar. And then you're measuring then, how much does it take? How much carbon do you have to burn in your civilization to produce a certain amount of goods and services? And your book actually takes a little bit of time to pick apart this idea of T, the greenhouse gas intensity, and point out that it is actually another variable, EI, times a quantity CI, where EI is the energy intensity, which is like how much energy it takes to produce a dollar's worth of goods and services, and CI is the carbon intensity, which is how many tons of carbon it takes to make a joule of energy. Because that's actually the two different factors that go into this, right? How much energy it took to make those goods and services, and how efficient you were at making the energy in terms of how much carbon it took. If you could have a lot of your power from renewable sources like wind or solar or something like that, or other power sources that we'll be learning about later in the course, you have some measure of control over T in ways that you might not have over P or A. Or for that matter, you can make T go down where you're not necessarily, I don't think we want population to crash, I don't think we want affluence to crash. And so this is kind of the term we have some control over more directly. And if you actually work out this, it comes up that the equation for I comes up to having units of tons of carbon per year or something like that. Again, I think in your book they did it without the per year, so it was just tons of carbon being added, but whatever. So if you expand that T into the energy intensity and the carbon intensity though, you can see the trap that this equation reveals. This relatively simple equation shows us just how hard it's going to be to address our problems of how much carbon we're adding to the atmosphere and therefore how we are changing the climate. Let's look at that EI term. EI is about the amount of energy it takes to produce a dollar's worth of goods and services, and it's intrinsically what businesses do to try to drive that down, right? The more efficiently they can make the product, the less it costs them, the more profitable it can be, and so on. That is an intrinsically good thing, and we can fight that all we want, but we can keep making incremental improvements to the efficiency at which we produce goods and services. And that CI, the carbon intensity, is about how much carbon it took to make a joule of that energy that you use to make goods and services. Well, we could make our power plants more efficient, that would improve this term, or we could be using more renewable powers like solar and wind and so on, that would improve this term, and that's all intrinsically good too. And we can make incremental improvements in that as well. But notice that we're multiplying those two terms we have some control over, and we can make somewhat smaller, EI and CI, and we're multiplying them by P. P is a big number, the population, and it's a number that is only going up, at least in our frame, right? Obviously we're going to talk about the possibility that the population may start to decrease and so on, but for the near future anyway, we're multiplying those numbers by a big number that's only getting bigger. The math gets even worse, because then we multiply that by A, the affluence, which is a measure of, the total amount of goods and services that each person is consuming or producing or whatever, and that's only going up too. Okay, it is part of what is wonderful about our world, that we are reducing hunger, that we are making technology more available and so on, but that is also increasing the number of consumers in the world and their access to healthcare and food and all that, which is also wonderful, but we have to know how that's affecting climate. Well, look how math is a disaster here. P and A are big terms that are getting bigger fast. The terms that we have some control over and are trying to make smaller only can get small slowly. No matter what, the math here is working against us. No wonder back when we had that lecture about the scenarios, where we were looking at all the different ways in which carbon might change in the near future, we're going to kind of review a little bit of that in just a few minutes. No wonder it was a disaster, even for the best scenarios. the iPad relationship is actually a very, very tricky thing to work with. It's very hard to figure out how to make the total amount of carbon you're emitting go down in that equation. Now, to some extent, the best thing we can do with that iPad relation, though, on the other hand, is to see how these factors can change and the total amount of carbon we emit can change throughout the rest of the 21st century. In order to do that, you have to know how all the terms are going to be changing in the 21st century. Well, population is, in and of itself, a tricky one. In our history, for all intents and purposes, population has never fallen. Maybe a little bit associated with each of the world wars and things like that. But overall, the grand sweep of history shows population only increasing with exponential growth. And there are different models as to how that might continue. Maybe, as just shown in the green curve there, maybe by about the year 2050, population will reach a peak of around 8 to 9 billion, and then begin to decrease. This happens because as currently underdeveloped nations become more developed, as women have more access to health care and education and so on, generally birth rates fall, and then we will have a falling population for the decades of the second half of the 21st century. But that's not necessarily the case. You make very small changes to your approximations to things like fertility rates and fecundity rates and so on, and you get a population that will eventually peak, but not well until the 22nd century. Well, the difference between that orange curve and that green curve is a couple billion people. That's a big change in the total amount of carbon that's going to be emitted in the atmosphere. And for that matter, I mean, you can make a few more changes as to like the availability of education and fertility rates and things like that, and you can get that red curve where no place in the foreseeable future does the populations begin to decrease. None of which might be, all of which might be good news, all of which might be bad news. We don't know what the future holds for these population changes and so on. What we know is that the range is huge. The green curve that's on there is the so-called best estimate of what population is going to do over the next 100 years, but the curves look very different. And 100 years from now, the population could be anywhere from 5 or 6 billion to 20 billion, depending on the exact ways in which things like fertility rates and fecundity rates and so on change. We have to be prepared for that. It does no good to not think about how population could change if we're going to be dealing with the issues of climate change. Also, there's a whole business of issues of affluence, okay? If there's going to be 9 billion of us in the world in the year 2050, we want those people to have some kind of quality of life. We don't want them starving, begging, not having access to health care, not having access to education, etc. But affluence is a really complicated idea. I mean, it depends on so many factors like education, social justice, international security, the rule of law, free trade. I wrote on here a few others that I found in papers: access to technology, monetary policy, things like inflation and so on, immigration patterns, and many, many, many more. Actually, making some kind of estimate of what the global value of affluence is going to be is really very tricky. On the other hand, in the past, different, all of these factors have kind of also been varying a lot from region to region. Okay, maybe the West had a greater increase of affluence, whereas the South was gaining in affluence more slowly or something like that. That makes it really hard to come up with good estimates of what the future's affluence is. On the other hand, we can. I mean, that's what a big part of economics is. That's a big part of what sociology is, and so on. And based on that, on the work of those scholars there, we have some pretty good ideas. We have the idea that if you're a developing nation, like India, China, Indonesia, and so on, we could expect that over the next 100 years or so, the best estimate is somewhere in the range of 2 to 3% per year of affluence increase. That's a pretty sizable rate of improvement of quality of life. And that is intrinsically a good thing. The problem, of course, is if that increase in affluence comes at the price of having a lot of greenhouse gas emissions, then we have a big problem. In contrast, for the industrialized nations, there's still an improvement in affluence too, but it's much, much slower. More like 1 to 2% per year. The gains are just going to be much more incremental for the developed nations than they are for the developing nations. The gap, it would appear that the best guess is that the gap between the rich and the poor is going to be getting smaller. Again, intrinsically a good thing. It's just something, though, that has to be managed so that we understand what it means with regard to global warming and so on. How about technology? That was the other one that was on that curve. Now remember, in this context, we're not talking about beep boop technology. We mean like techniques and methods and practices and so on that are about how we use carbon to produce energy to produce goods and services. And the idea is to, find ways to make that all more efficient. And what we know is that over the last few decades, just due to market pressures and incentives and so on, globally the ability to produce goods and services has become more efficient at a rate of about 1% per year. And as far as we can tell, there are no revolutionary technologies on the horizon. It isn't like we are this close to developing cold fusion and then all that energy will be free with no carbon, or that close to being able to scale up wind power so that all that power will be coming from a renewable source. We don't need to worry about the greenhouse gases anymore or anything like that. There are no big revolutions like that anywhere soon. So it's probably reasonable to assume if you're going to make a little model that's going to be telling you about how carbon is going to be changing, you might as well assume that we're going to continue to improve our efficiency by about 1% per year. Okay, we're going to take all that information and decide what that means for for carbon and other atmospheric constituents into the 21st century, but before that, let's answer a couple quick questions. Question 1. Why does population matter when estimating the amount of greenhouse gas emissions in the future? Is it A, because more people means more respiration, and therefore more emission of carbon dioxide? Is it B, because more people means more consumers, and therefore more combustion of fossil fuels? Or does it mean C, more people means more coastal residents, and therefore more people displaced by sea level increases? Which of those is the real reason why the IPAT relationship has to include a factor for population? Make a choice from one of those three and get a little feedback before you move on to question 2.